get class underway. All right. So the first problem I was going to do, I'm pretty sure I skipped this problem. Does everybody agree with that? The x, e to the x minus 2. This is under the closed interval method. So I just need to differentiate this guy. That's my first task. This is a product. So I'm going to differentiate x, which gives me 1, plus, leave the x, derivative of e to the minus x over 2 is minus 1/2 e to the minus x over 2. So if you really wanted, you could write it like this. Excuse me. So the first thing we had to do was take the derivative. The second is then to go ahead and find the critical values. To do that, remember that we have to set the first derivative to 0. So I'm guessing if you guys tried this at home, you might have gotten a little confused because you said to yourself, okay, I've got to make this guy equal to 0 and this equal to 0. Well, this is an exponential, right? It's e to a power. You may recall that that graph looks something like this. Or for a negative, it looks like that. So my question to you then is there any way to make this e to a power 0? So go ahead and take a second. Some of you give me an answer over here, what you think. So either the stream went down, the chat's really slow, or you guys just don't want to answer me, which is normal. So this exponential, right, if we look at the graph, can never go to 0. So there's no way for this thing to be 0, which means we don't have to worry about it. We just got to solve this piece. And that's really easy, right? This just gives us x over 2 is equal to 1, or x is equal to 2. So that's my critical value. And you really need to recall how to do that because we're going to use that in the next stuff that we do. So all we did was take derivative, set it to 0, solve for x. Now I need to take that, as long as it falls between my endpoints and the endpoints, and plug them into the original. So can someone do that for me and give me the values? So of 0, that one's easy. That one's 0. Actually, this isn't too bad. If we plug in 2, right, this is e to the minus 1. So we get 2 over e. And then this one's going to be 5 over e to the 5 halves. So if you could give me some decimals for those, or I can calculate them real quick. As soon as I locate my calculator, here we go. So 2 over e is 0.736, let's say. And then 5 divided by e to the 5 halves is 0.410. So by the closed interval theorem, 2 over e, if I plug 2 into the original function, there's a 2 there for the x, and then this would be e to the minus 2 divided by 2. That's a negative 1. So e to the negative 1 goes in the denominator. So the closed interval theorem now says which one of these values is the largest, which is the smallest. They will tell you what is your absolute max on that interval and your absolute min. So one thing I wanted to say was this only works for closed intervals. So if I were to ask you, find the absolute min and max of this function over all real numbers, right, that would be very difficult to do if a function allowed all real numbers to be plugged in. So this is really, you can only find the absolutes over some small interval. Now, of course, we could do larger intervals if we use a computer, but the only way we can find absolutes is over some interval that is not all real numbers. So that was the closed interval theorem. We then did Rolle's theorem. And Rolle's theorem says that if you test the endpoints in the original function and the value of y is equal and the original function is continuous and differentiable, there had to be some point in the center or somewhere between a and b, I shouldn't say in the center, where c, which is just some value of x, gives you a slope of 0. Now this is generalized. It says that they both go through the axis, right? They don't have to do that. They could be this point up here and this point up here at A and B, and then this point right here could be C. So let's see, which one did I not do here? Did I do the first one? I think maybe I did both of these. Somebody want to remind me what they have in their notes really quick? Or if you'd like, I can just do this one over really quick. I think actually this one I ran into some trouble, didn't I? So let's check this. Let's go to good old Mathematica real quick. And we can plot this guy. Right, and this is a good practice for you if you're doing the problems. You can always plot them to give you an idea of where the point is that you're looking for. But you still have to prove that you can do it analytically, but that doesn't mean that you can't check yourself doing it this way. So I'm going to plot the function that we have here, which is x cubed minus 2x squared minus 8x. It says from -2 to 4. So it appears that there are 2 points such that this occurs. So did I find these 2 points for you? Yeah, that's what I thought. I thought that I ran into a something silly. So let's just do this one really quick. We want to find f prime. Right, this is a polynomial. It is therefore continuous and differentiable from -infinity to infinity. That means this guy works just fine, which means I shouldn't have run into any problems. So let's see if we can figure out what happened. So we have this, and first we tried to factor, and then that didn't work, so we went to the quadratic formula, right? So that's opposite of b plus or minus the square root of b squared minus 4 times a times c. I think that was my problem, is I forgot to make that a -8. So all over 2 times 3. So everybody can see that all right? Okay. All right, so that was my silly mistake. I forgot to plug in a negative there. That was our problem. All right, so I'm going to do this, and you can do this any way you like, however you like to simplify. I noticed there's a 16 there. If I take a 4 out of this 8 and multiply by that 4, that's also a 16. So they have 16 in common. If I factor 16 out there, I have a 1. These two negatives make it a plus. And then left behind would just be 3 times 2, because we took a 4 out of this. So 6 all over 6. So we're going to get 4 plus or minus. A 4 can come out of the radical. Square root of 7 all over 6, and then reduce everything. So that is 2 plus or minus 2 root 7 all over 3. Ugly, but there nonetheless. So let me calculate the positive one and see if it falls here. So that is 2 plus 2 times the square root of 7 all divided by 3. It's 2.43 something. So if I come over here, this looks like 2.2, 2.4. That looks pretty close, yeah. The other one you just put a minus sign there, divide by 3, and I get negative 1.097. So negative 1.09 something would be right around there. So yeah. So just a simple, silly error in sign. Now, of course, for Rolle's theorem, we also had to prove that the endpoints were equal, but we had already done that, right? So f of negative 2 was equal to f of 4. And we can see that pretty easily here on the graph. F of negative 2, f of positive 4, they both appear to be 0. So hopefully that helped with that problem. I can bring this guy back over. So that's a review of the two theorems that we've already done. We just need to do mean value theorem. Morning, Armando. All right, so mean value theorem is, as I said, more of a generalized form of Rolle's because the endpoints are not equal in value now for their y values. But that means that instead of a slope of 0 somewhere, we can find a point where the slope has to be the same as the slope between those endpoints. So this time, we have, so for Rolle's theorem, we are just finding the middle point of the function and seeing if, yes, you check the endpoints are the same. You also must prove that it's continuous and differentiable, which I had done the other day, so I didn't take time to do that, but I should have. I did mention it with the domains. And then you're finding some point between the endpoints of the problem. Not always necessarily the middle. I kind of have to be a little more conscious of saying that sort of thing. Such that the slope is 0 for Rolle's theorem. For the mean value theorem, we're looking for the derivative that equals the slope of the endpoints. So let me demonstrate. Sorry, I need to take some allergy medicine. All right. So we've got this function here. We first have to prove continuous, differentiable. So how do I prove that it's continuous? Well, the domain of this function, because it's a polynomial, minus infinity to infinity. Negative 1 to 1 certainly fits in that domain. So because this is in the domain, it is continuous. That's the first thing we had to show. The second thing was differentiable. So it has to have a derivative, and that derivative has to exist for all numbers within the interval given. So this is domain of f. What's going to be the domain of f prime? Well, let's go ahead and find f prime. So f prime is 3x squared minus 2x minus 2. Pretty straightforward. Domain of that function, again, because it is a polynomial, is minus infinity to infinity. Same reasoning, differentiable. Okay, so we've checked off that it's continuous and differentiable. Now the theorem says there must be some point where the derivative equals the slope between these two endpoints. So let's find the slope here. To do that, right, these are both, this is, say, x1 and this is x2. Well, we still need y1 and y2. So we need to take these guys, plug them into the original. So what happens if we plug 1 in? Well, we get 1 cubed minus 1 squared minus 2 times 1. So f of 1 is going to be 1 minus 2, or minus 2. F of negative 1 is going to be negative 1 cubed minus negative 1 squared minus 2 times negative 1. Negative 1 cubed is negative 1. Negative 1 squared is positive, but then that guy makes it negative again. And then these two make a positive. So it looks like this one comes out to 0. So question, why is negative 1, 1 equal to the x values and not x1, y1? So this is an interval that they gave us. So that's really telling us, right, and I don't know exactly what this function looks like. It is a cubic, so I'm just going to assume it looks something like this. In general, that's telling me I only care about from here to here. So from 1 to negative 1. Those are definitely x values for that. So that isn't a coordinate, right? It's not an x1, y1. This is in fact the interval. The parentheses here tell us that it's not defined at the endpoints, or that we just don't equal the values at the endpoints. Right, we could have an interval like this, technically. So that's just interval notation for x1 and y1. So our 2 points now are 1 and negative 2 and negative 1 and 0. So we need to find the slope for those 2 points. So I'm going to do negative 2 minus 0 all over 1 minus a negative 1. So that's negative 2 all over 2, because that's really a plus. And that gives me my slope is negative 1. So the mean value theorem tells us that once we find this slope, there's got to be some point that we can solve for here for x, such that the slope of the line between these two endpoints is the same as the slope of the tangent line to the curve. So I need to set these two things equal. So any questions about this so far? I know it's a lot of steps to remember, but they're not They're not super tedious, and they're not really technical, let's say. They're just kind of, do one, do the other, and go from there. All right, so if I want to solve this guy now, I'm going to go ahead and move this to the other side. So I've got 3x squared minus 2x minus 1 is equal to 0. Because if I move this to the other side, it becomes plus 1. So we could try to do this by grouping. We're looking for two numbers that multiply to -3 and add to -2. So multiply to -3, add to -2. I believe -3 and +1 will do that for us. That means I can go ahead and replace the middle term here by these two. So I'm going to bring down the 3x squared. I'm going to bring down the -1. I'm going to replace the -2x with a -3x plus x. Then I'm going to group the first two terms and the last two terms. Making sure to leave a plus in between there. So now in common in the first two, I have a 3x, leaving behind an x minus 1. And over here, I've already got x minus 1, so I just have to realize there's a 1 outside there. So far I've factored it to that. And then to finish up, let me just go up here. The two factors are everything on the outside and everything on the inside, which have to be the same, right? If these aren't the same, then you've done this incorrectly. And then last step is to go ahead and solve for x. This one's really easy. It's going to give me x equal 1. This one over here is going to give me x equals minus 1/3. Now it's important to note that the interval given was -1, 1, and we were not equal. So when we got x equal 1 over here, that doesn't work. Not sure if that guy showed up or not. See what this little blue one does. You see that x? So let me go back through the process really quick. We had to first prove continuous and differentiable. We did that by looking at the function. It's a polynomial. Its domain is -infinity to infinity. Our interval is only -1 to 1. That's clearly within that domain. Therefore, the function is continuous over that interval. Then the derivative, must be differentiable over that interval. And to do that, we have to prove that first we can find the derivative, which is typically always the case. And then we need to show that it has a domain that contains this interval. Again, a polynomial easily contains that interval. So both continuous and differentiable. The next part was to find the slope between the endpoints, but of course we had to find those points. We were only given x values, so we took the x values, we plugged them into the original function, and got the two y values, resulting in our 2 points. We took those 2 points, found the slope. Once we had that, we take that slope and set it equal to our derivative, which is here. And then our task is to just solve for x. So we did, in this case, factor by grouping, came out with these 2 values. This one is not contained within the interval, therefore only this guy is the solution. Any questions about that problem? All right, glad it makes sense. Why did you set the slope equal to the derivative? That's the whole point of the mean value theorem. It says that there is some point between the 2 endpoints, the 2 x values, such that the slope of the tangent is equal to the slope between those points. So all that other stuff is just to prove that you can do it, and that's really the meat of the problem, is to set the slope equal to the derivative. All right, so let's see if there's any other problems besides this one that are left. Yeah, let's go ahead and do this guy. I think the arc sign will just confuse us for now, so let's go ahead and just go ahead and do this one. And then I would like to start the next section, which I think should be a nice easy progression now that we've done these problems. So how's everyone doing this morning? Say you're sick. Okay, sorry to hear that. Everybody's tired. Is it harder to stay awake when you're at home just watching me on a screen rather than in class? Anybody project this up on their TV? Have any fun with it? No need to disappoint. I'm not disappointed. I was just curious. All right. So we've got this function here. First question is, what's the domain? For the x portion, I can plug anything I like. The log, I can't. Natural log looks like this. So I can only plug positives and actually not 0. So the domain of my original function is x greater than 0, or if you wanted an interval notation, 0 to infinity. The domain of f prime, well, let's find f prime. So this is a product. Derivative of x is 1 times the natural log. We just leave it alone. Plus, leave the x alone. Derivative of natural log is 1 over the inside. And because this is just x, we just get 1 over x. And that simplifies to natural log of x plus 1. So again, the only values of x I can plug into the derivative, 0 to infinity. My interval here, clearly contained within those two, therefore continuous and differentiable. So we've proven those two things. So all we need to do now is find the two values of the function. All right, we need to plug 1 and e back into the original. So f of 1, f of e. So f of 1, that's going to be 1 times the natural log of 1. Natural log of 1 is just 0. So this is 0. And when you plug e in, you get e, natural log of e. Well, natural log of e is 1. So we get back e. So our 2 points are 1, 0, and e, e. So let's find the slope. Use this as my second point, so that's going to be e minus 0 divided by e minus 1. So e over e minus 1 is my slope. All right, so then I need to take my derivative, which is natural log of x plus 1, and set it equal to this. I would subtract 1 over here. And then ironically take e of the whole thing. Let's see if we might be able to simplify this first. So this is going to be e minus an e minus 1 all over e minus 1. These e's would cancel, and we would get, let me just come back over here, easier for you to see, we would have natural log of x is equal to 1 over e minus 1. And I want x, so I've got to do e of both sides. So I get x equals e. I'm going to write this e, you can commonly write as exp. So I'm going to write it that way. Of 1 over e minus 1. So that just means when you plug it in the calculator, you would type e to the power 1 over e minus 1. So I'm going to go ahead and do that just so we have an idea of what that number looks like. It says 1.7895. So let's just say 1.8 approximately. And I just wanted to know that because I wanted to make sure, does it fall between 1 and e? Otherwise, we've done something wrong. So question says, why did you take e of the whole thing? Is it because of the log? Absolutely. I had to get rid of that log of x. To get rid of the log, I have to take and raise everything by e. Everybody okay with that? Thanks for responding. Anybody else want to say something? Yep, no problem. All right, so I'm going to assume you guys are good. And we can move on to the next section. So also don't forget that I put suggested homework assignments on Blackboard. So if you guys want problems to try and you don't have your textbook, or you can obviously Google stuff, but there are problems there already for you guys to try, and the solutions should be there as well. So that should be a helpful resource for you. Oh man, that focus just went all crazy there. Okay. Pretty sure that was the last problem in that packet. So let's go ahead and close that guy out. And drag this one over. Increase the size slightly. Okay. Somehow it's all the way at the bottom. All right. Let me just get my chat back. Okay. All right. So we just got done doing all those theorems, and those are kind of a lead into what we're going to do next, which is the first and second derivative tests. And all of this is to get us to be able to plot a function without graphing. So the first derivative test tells us if a function is increasing or decreasing. So notice it says here if the derivative is greater than 0. Right, it might be a little hard to see, but that is an f prime. So it says if f prime is greater than 0, then f is increasing over that interval. And if f prime on that interval is less than 0, then it's decreasing. So what does that mean? Well, if you think about it, right, f prime, that's the slope of the tangent line. And if it's greater than 0 or positive, right, we all know that positive slopes look something like this, right? So I just made a curve here, right? The slopes on that curve are all positive, and notice the only way for me to draw that curve was as though it was increasing. And then if I keep going and bring it down this way, what do my slopes look like there? Well, they're now negative. So the negative slopes indicate that it's decreasing. Now the way to do this is it says find the derivative and the critical value. So remember, we have to take the derivative, set it to 0. So this means f prime equals 0. We do that, and that's going to tell us all of the places where the derivative, right, the slope, is 0. Most times, the slopes change if the graph has a slope of 0 somewhere. So here we went from positive to negative, and somewhere in between it had to be 0. You can't have cases where you're increasing, go to 0, and keep increasing. So that's not always the case. But if you see a sign change, that also tells us something about the graph. So we'll talk about that. Next thing says set up a sign chart. So what I like to do is set up a little chart for the signs on the derivative and set up a number line which is broken up by the critical values. And then using all that information, determining where the function is increasing and decreasing. So let me go ahead and do a problem, demonstrate, and see if any of that makes sense. So my equation is x cubed minus 6x squared plus 9x. And the first thing I have to do is find the derivative. So f prime of x is 3x squared minus 12x plus 9. Okay? Now I need to set that to 0 to find the critical values. So equals 0. I notice each one of these terms has a 3 in common. I'm going to factor that out. And then if I were to just divide by 3, that'll disappear. So I've got x squared minus 4x plus 3 equals 0. That can be factored, I believe. So let's see, we need two numbers that multiply to positive 3. and add to -4. So -1 and -3. So x minus 1, x minus 3, right? Because these are going to give us +3 when multiplied, and add to a -4. Still equals 0. That very easily gives us x equals 1, x equals 3. These are our critical values, or if you prefer, critical numbers. So I need to set up a number line that involves those values. So I have 1 and 3. I'm going to put an arrow down to those. So effectively, right, this is a polynomial. I'm allowed to plug any value of x I like in there. And so in this case, I have taken my interval, which is -infinity to infinity, and I've broken it into 3 pieces, right? I've got -infinity to 1, 1 to 3, and 3 to infinity. My job now is to say, what is the sign of the slope in all 3 regions? We know that the slope at 1 and 3 is 0. So, I need to pick test points. Pick the easiest ones possible. A number smaller than 1 is 0. A number between 1 and 3 is 2. And a number bigger than 3 is 4. All right. Now I need to go back to my derivative. I'm going to take the form that is factored, but I also have to keep in mind that there was a 3 there. In this case, that does not matter. However, if that was, say, a -3 that I factored out, that will make a difference. So, my chart, okay, I'm going to have my test values x, which are 0, 2, and 3. I'm also going to have all of the components of my derivative. That would be 3 x minus 1, x minus 3, and then finally I need a column for the product, right? Because all 3 of these things are technically multiplied together to give me my derivative. Everybody with me so far? So I'll pause for a second. Please, a couple people answer me. Make sure that you're understanding what I've done so far. All right, so just a few people there. All right. So now I need to say, all right, if I plug 0 into these pieces, what are their signs? I don't care what the number is. I just want to know what's the sign. Well, 3, that's just a number. So I can't really plug them in. It's always positive. That's why I said in this case it doesn't matter. If it were a -3, we'd have all negatives here. All right, plug 0 into this. 0 minus 1. Well, that's a negative number. That's -1. So negative. 2 minus 1. That's a positive number. And then 3 minus 1. positive number. Now plug all of them into x minus 3. Plug 0 in here. I'm using 0 to... sorry, that should be 4. Nice catch, Naya. I apologize. Right, these are my 0 points. I need the ones that I chose for my test points. Sorry about that. All right, so again, if I plug 4 in there, that's still a positive number, so we're okay there. Would have noticed when we got down here, right, if we plugged 3 in, we would have gotten a 0, and that doesn't have a sign necessarily. So that would have been an indicator that we did something incorrectly. So plug 0 in here, that is negative. Plug a 2 in there, negative. Plug 4 in there, positive. So now, look at the signs and say what would be the sign of the product. So if I multiply a positive times 2 negatives, I get a positive. So again, this column really doesn't matter in this case. I'm just going to look here. So positive times negative, negative, positive times positive, positive. So we take those, put them up here on our number line. So 0, derivative was positive. The region that contained 2 is negative. The region that contains 4, positive. All right, so what good was all that? Well, now we can say, I know what the sign of the derivative is, and I can tell you where it's increasing and decreasing. It's increasing where I see a plus, and it's decreasing where I see a minus. So, increase from minus infinity to 1, right up to the critical value. It's also increasing from 3 on, or 3 to infinity. It is decreasing between the two critical values, 1 and 3. You should never use brackets for these. You should always have parentheses. So really quickly, I just want to plot that polynomial for you so that you can see that we proved where it was positive and negative. So that function is x cubed minus 6x squared plus 9x. And the interval that we have to go over is, let's say, I don't know, minus 5 to 5 should give us enough, or maybe let's go to 6. Actually, let's not go minus 5. Let's go minus 2. Much better. Okay. So this is the plot of the function that we just looked at. We said that we were increasing from negative infinity up to 1. So every 2 ticks here is a whole number. So 1 is right here. So it says that the function has positive slope and therefore is increasing up to that point. From that point to 3, we're decreasing. Here is 3. And then from 3 on, we're increasing. So that's what we just looked at. Any questions about that guy? So I really like to plot these for you because it really drives home what we did. And it doesn't necessarily always make sense to just look at the numbers. I hope that that helped a little bit. All right, so let's go ahead and try this one. So first thing we got to do is find the derivative and then the critical values. So that is x squared over x squared minus 4, in case you're having a little bit of trouble seeing that guy. I noticed looks like some extra glare has started. I think maybe some depressions in the board start to do that. All right. So I want f prime. This is a quotient, so I'm going to do low times d high minus high. Derivative of low is just 2x all over x squared minus 4. Now I see that both of these have a 2x in them, so rather than multiply it all in and then subtract, I'm going to go ahead and factor out that 2x. That's going to leave behind x squared minus 4 and a minus x squared. Which makes it real easy to get rid of those x squareds. I then have 2x times a negative 4. So I really have minus 8x over x squared minus 4. So just a quick question. See if you guys are paying attention / learning something. How do I find the critical values for this equation? So go ahead and answer me in the chat there and tell me what you guys think. We talking about Naya was there the whole time. Set it to 0. What am I setting to 0? Yes, I get that I'm setting the derivative to 0. If that's the case, which portion of it? Set the derivative equal to 0 and then factor it, okay. So the reason I asked is most of the problems that we do, right, we always set the derivative to 0. However, because this is a quotient, when we set the derivative to 0, that's really just saying when's the numerator 0. However, critical numbers also occur when the denominator is 0, because we can also have undefined. So if you go way back to the beginning of that last packet, the definition for the critical values is when the derivative is 0 or does not exist, meaning undefined. And that's when denominator is 0. So we need to both solve this equals 0, right, the numerator, and we need to do this equal to 0. So yes, set both to 0 separately and solve. The first one, really nice, just tells me x is 0. That's one of my critical values. One on the bottom, right? It's squared. I can take square root both sides. I get this. I liked the suggestion of factoring. This is the difference of two squares. So that's x minus 2, x plus 2. Therefore, you get x equal negative and positive 2. So, critical values are negative 2, 0, and 2. All right, so now we need to set up a number line that is broken by these critical values. Then we need to decide on what we want for the test points. So between negative 2 and 0 would be a negative 1. Between 0 and 2, I would choose 1. And then outside of these, I would choose negative 3 and positive 3. So again, let's set up our little chart. We've got our values of x that we're going to test. Those are negative 3, negative 1, positive 1, and positive 3. Now I need to go back to my derivative. I'm going to break this up so that there are two parts. The two parts are the numerator, negative 8x, and you can do this however you like, as long as you, I mean, you could do all at once, just plug the number in, that's up to you. So I'm going to let negative 8x be one piece. The other piece is going to be 1 over x squared minus 4 squared. And I write it that way because I still want to write this as the product. I still want it to be the multiplication of the two things. So negative 8x times this gives me back my original derivative. Now this problem is also quite special. And the reason for this is, rather than torture you and make you plug all four of these numbers in, notice that here I'm squaring x, which is always going to be positive. However, it doesn't mean that subtracting 4 from the number is going to be positive. However, we've got this square out here. This square here makes it such that this is always positive. So I just want to see, you guys able to see that square there? Yeah, it looks okay. So this portion of the derivative, regardless of the value of x that I plug in there, is always positive, because I'm squaring it, right? So any squared value, whether it be negative or positive, always positive. So I really only have to care about this piece. Well, it's negative 8 times a negative number, that's positive. And a negative 8 times a positive number is negative. So positive, positive, multiplied together is positive. Negative and positives give me negative. So if I go back and put these on the chart, I am positive in those two regions, negative in those two regions. Now, I'll tell you right now, one of the biggest things I see students do is they go, oh, well, it's positive all over here, so I'm just going to say from minus infinity to 0. We can't do that. Remember that we found these guys right here, and that was because they were where the derivative was undefined. Well, they also happen to make the function undefined. Right, if I plug 2 in there, 2 squared minus 4, that's 0. So I'm dividing by 0. So those are actually asymptotes of the original function as well. And so when I write my intervals, I can't include those points. So I have to write increasing minus infinity to -2 and -2 to 0. Then I would put decreasing from 0 to 2 and 2 to infinity. So that is what I was trying to get to. So again, I would like to plot that for you, and I would like to point out one other thing here. So while I'm plotting this, please, if you have any questions, go ahead and ask them now. All right. So here's the plot. Let's see if maybe we can find a spot on the screen where we can still see it behind all the work. So notice we said it is increasing from -infinity to -2. So -infinity to -2. Then it has to have a break because there is an asymptote. And it's increasing from -2 to 0. -2 to 0. Then we said it decreases 0 to 2 and 2 to infinity. So it looks like this is good for the plot. The other thing I wanted to point out, we used that theorem to find the absolute max and mins. Well, here we don't have necessarily a defined interval, right? We've got that we could possibly pick up all real numbers. So we can only find what's called the local max and local min. And the first derivative test helps us with that. Notice we had a sign change from positive to negative here. That means that this guy, this critical value, is either a local max or a local min. So by local, we mean that it's either bigger or smaller than all the values around it. So clearly from the plot here, at 0, this point is a local maximum. And that should make sense. If I go from a positive slope to negative slopes, I should have a maximum. If I went from negative slopes to positive slopes, I'd have a minimum. So anytime you have a sign change here, there is the potential for a local max or a local min. So that's even more information that the first derivative test gives us. How are we doing on time? 9:20. Got plenty of time. Everyone's stream working okay today? Alright, I guess let's go ahead and do this guy. I'm going to do this one a little bit faster since we've done the process a few times. So let's make note at the beginning of the problem. What's the domain of this function? Well, natural log doesn't allow me to plug in negatives, doesn't allow me to plug in 0. This would allow me to plug in 0, but that one tells me I cannot. So the most restrictive part is the natural log. So we can only plug 0 to infinity, not including 0. So that's going to be important when we get our critical values, I believe, for this problem. So again, let's start by finding f prime. This is again a product, so if you like, you can rewrite it as x to the 1/2 natural log x. Let's go ahead and differentiate this guy first. That's 1/2 x to the minus 1/2, leaving natural log alone. Then add to that, leave the square root alone, or the x to the 1/2, excuse me, and derivative of x, natural log of x is 1 over x. So actually let's leave this as x to the 1/2. Alright, so I just want to rewrite this. This is going to be natural log of x over, 2 stays down here, x to the minus 1/2 really means put that in the denominator and make it a square root. And then x to the 1/2 over x, that is really 1 over root x. So we could put these together, right? I can multiply this by 2 over 2, and this becomes natural log of x plus 2 over 2 root x. So that's my derivative, and I wanted to write it that way so that it was pretty clear as to where the function would be undefined. So again, because it's a ratio, I need to set natural log of x plus 2 to 0, and I need to set 2 root x to 0. Well, this one right here gives me natural log of x equal to -2. Take e of both sides, and so we get x equal e to the minus 2. And then this one is x equals 0. But recall, we do not include 0 here in the domain, so this is not really a critical number. We've only got this guy. So when we do our number line, we've only got this e to the -2. So let me just calculate a decimal for that, so we have an idea what the numbers around it look like. That is 0.135 to a 3 decimal place approximation. We cannot use 0, right? And technically this number line doesn't go on forever. It stops at 0. So because this is 0.135, I think I'm going to use 0.1 on this side. And then over here, I'm just going to use 1. That's a nice, easy number. This is my critical value there. Make up my little chart. I've only got 2 test values this time. Those are 0.1 and 1. Then my derivative on top is natural log of x plus 2. The bottom is 2 root x. And I'll just write p here for product. So this time I'm going to use the calculator to calculate log of 0.1. I know it's negative, I just wasn't sure if it was greater than 2. It is. Therefore, this number is negative. And if I plug 0.1 into that, it's positive. Therefore, the product is negative. Log of 1 is 0, so this is positive, and this is positive, and therefore the product is positive. So if I go back to my number line, negative there, positive there, therefore it is increasing from e to the negative 2 to infinity, and decreasing on the small interval 0 to e to the minus 2. So while I'm plotting this, just to show it to you, tell me, we see a change in sign here. What is this point? Is it a local max or a local min? All right, so I see somebody said local min. Anybody else want to answer? All right, I guess not. So I will show you the picture, which looks like this, kind of like the Nike symbol, if you will. So we said it's increasing from e to the minus 2 to infinity, so this value right here is approximately e to the minus 2. It's increasing from then on, and it decreased from 0 to e to the minus 2, so from here down it's decreasing. So yes, this is a local min, which we were told by the change in sign here in the first derivative from a negative to a positive. So that allows us to now go on to the second derivative test. So I can at least introduce that to you today and hopefully do that. Next time we can work on graphing without a calculator. So we'll be putting all of this stuff together. So the second derivative test is often referred to as the concavity test, or concavity, however you like to say it. And this requires that we look at the second derivative, or double prime, and it's the same thing. We're looking for the double prime to be greater than 0, but instead of increasing, it tells us concave up. And if the second derivative is negative or less than 0, we're looking for something that's concave down. So what does concave mean? This is concave up, this is concave down. So maybe if you need to, remember the up, the U shape, right? But I don't have to have the complete shape. I could just have this, that's concave up, that's concave down, okay? So very similar to how we did the, and let me change this wording here real quick. I noticed this says for the second derivative, find the critical values. We want to call these instead inflection points. We are finding them in the same manner. We are still taking the derivative. We're still going to do our number line, and we're still going to look at our chart. So everything is pretty much the same, just now with the second derivative. So again, let me demonstrate. I need to first find f prime. That's going to be 15x to the fourth minus 15x squared, and then plus nothing, right? It's a constant. Derivative gives us 0. Then, if I really wanted, I could write it like that, so that the second derivative, right, I can just leave this 15 out here, and then the derivative of x to the fourth is 4x cubed. Derivative of x squared is minus 2x. And then I might go ahead and maybe factor out a 2 and an x. So I have that. You can again do that any way you like. If you don't like the way my mind works in terms of algebra, feel free to try that a different way. Just make sure you get this guy. So that's my second derivative. I need to then set that to 0. So that means 30x could be 0, or 2x squared minus 1 could be 0. This is pretty clearly going to give me x equals 0. This one's going to give me x squared equals 1/2, or x equals plus or minus the square root of 1/2. So instead of calling these critical values, these are the inflection points now. and this is 0, negative square root of 1/2, and positive square root 1/2. Okay, so number line, just like before, break it up with these values. So we have 0, we have negative square root of 1/2, and square root of 1/2. Again, let me look at the, oh, hey kitty. Great, thank you. Hope you feel better. Let me go ahead and plug these in the calculator again to give us an idea of the values. You guys gotta love the unscripted teaching from home bits, huh? Yes, the cat did. Thanks, James. And right where I've been stepping as well. So this is approximately 0.707. I should have remembered that off the top of my head. So I can choose, I'm going to choose 1/2, negative 1/2, negative 1, positive 1. So let's make the chart. Appreciate that you guys are most active now about the cat more than you have been the whole time. So I've got my values there. The parts of my derivative were 30x and 2x squared minus 1, and then the product right. Take these numbers, plug them in. So if I plug a negative into this portion, it's going to be negative. Plug a positive in, I get positive. This one we got to be careful. Negative 1 squared is positive 1. That's 2 minus 1, which is a positive. Product, negative. Plug in a negative 1/2. Well, I square the square root, I get 1/2. 2 times a half. Oops, I plugged in the roots. I don't want the roots. Darn it. All right, we got 0 again, so don't want to do that. I started to plug in my inflection point instead of the test point. Silly me. I got flustered by the cat. All right. So, sorry. Let's plug the negative 1/2 in there. Square that. That's 1/4. 2 times a fourth is 1/2. 1/2 minus 1, negative. Plug a 1/2 in. You still get negative. And plug in a positive 1. You get a positive. So my products are negative, positive, negative, positive. Put them on the chart. And then just go ahead and state where it is concave up and concave down. So concave up, negative square root. Give myself some more space there so it's clear. It's negative square root to 0 and square root to infinity. And then Sorry, you can't see that. There it is. And then concave down is going to be from minus infinity up to the radical, and from 0 to the radical. So same exact process, just have to take the second derivative. Any questions about that problem? So we've only got about 7 minutes left. I'm going to say let's go ahead and just, I'll leave the rest of the time if you guys have questions for me. Please try the next problem for next time, the x e to the 2x, and possibly give this one a shot as well on your own. I will go ahead and post a quiz for you, and I would like you guys to send that back to me by let's say Friday night at midnight, and I will get these tests graded for you. So yes, I just mentioned about a quiz, so I'm going to go ahead and put that up as soon as we're done here. I'm going to go ahead and stop the recording.